So let's continue. This is the last part of our discussion on atoms. Although we will do some atomic physics, continue on, but that has to do with how an atom interacts with light. Okay, so that is a different that will be a more involved topic that has to do with time-dependent perturbation. So we will do some of them next week. So this last part is about the periodic table. So the main message is the Schrödinger equation. We know how to write down n electron atom Hamiltonian, no doubt about it. And we realize that we cannot solve any one of them, but we have discussed the philosophy of simplifying such many electron problems into independent particle approximation treatment, but in a rather involved way, for example, self-consistency, etc. At the end, this saves a lot of effort. We can retain or rescue the idea of atomic orbitals. We have 1s, 2s, 2p. We still have this hydrogen picture to play with. But we realize that on the outset, they look simple. But if you really go into atomic physics and do such calculation, it is quite a big research area. And with this, the antisymmetric requirement of the total wave function, whatever way you treat the wave function, also leads to the Pauli exclusion principle in the context of single particle states. We have this Slater determinant that already implied you cannot put two particles into the same independent particle states. Okay, so the first point is that with these tools in our mind, we can explain much of the physics of the atoms and the periodic table. Ground state, very simple. Just fill electrons into the atomic orbitals according to the Pauli exclusion principle. The periodic table has a long history. A few years ago, it was 150 years anniversary. So it was the International Year of Periodic Table a few years ago, declared by the United Nations. So this is the early form of a periodic table by Mendeleev. And this is the up-to-date version. I checked it a few days ago. This is still the latest formal version issued by this place. This is the International Union of Pure and Applied Chemistry, IUPAC. So every few years they will meet and then they will decide whether a new version of the periodic table should be released. Usually there may be one or two new elements found. So on this periodic table, it was up to 118. But these elements, where's 92? My eyes are not helping me. I think 92. 98. Here. Okay. So uranium is here. So after uranium, from this place onwards, 9103, and then go into here. Okay. These are short life elements. Usually through accelerator physics, they are formed for a very short time, but still long enough for experiments to be done to prove their property. So even up to now, I think there are big groups in Germany, in California, and also in Russia. They are aiming at making bigger and bigger atoms, extending the periodic table. But they are short life, so you will not find it naturally on Earth after uranium. Okay, so this is the version December the 1st, 2018. They have some funny name. The latest one are very. This is California. So of course it was discovered by the labs in California. This is Fermium. So maybe they suddenly found that they haven't honored Fermi, who did a lot of things on flying neutron into different things, all the other elements. That was the Nobel Prize awarded to Fermi for that work. So you also have mendelevium, that is in honor of this first version of the periodic table. Okay, if you discovered a new element, then in the meeting of IUPAC, then you can propose, I want to call it this way. This is livermorium, so again, a California product. Right? So periodicity. Periodic table means there's some periodicity in the physical properties of the element. So here are the standard ones. And I will also want to introduce this idea to prepare for our later discussion on molecules. So the first thing here, you see something called the ionization energy. More precisely, is the first ionization energy. That is to say, you take a neutral atom. How much energy you need to take one electron out, free one electron, and that becomes a +1 ion. That is the first ionization energy. So here is a plot of the first ionization energy in units of electron volt. That is physicist product. You see there are some going up, boom, come down, going up, boom, come down, and something like that. Okay, so you see, when it goes to a so-called closed shell structure, that atom is very stable, and it takes more energy to take one electron out to infinity to make this an ion. But the next element, this is element number 11. Okay, so sodium, in so-called electron configuration, it is 1s2, 2s2, 2p6. This is 3s1. So there's one electron in the so-called outer shell, well, farthest away from the nucleus, but still filled. It is the 3s atomic orbital. So this outermost electron is easily ionized. And we know when many sodium come together to form a solid, it is a metal. This electron being so easy to be freed, they can easily wander around when sodium come together to form a solid. And that is the conduction electrons. So you see this go up, come down. This is the so-called periodic feature in physical properties. I would also like to introduce electron affinity. This is how much energy will be gained when a neutral atom attracts one electron. So I think the most noticeable examples are in the fluorine, chlorine, those halogens. Traditionally, it's called the group 7. So fluoride, chloride, bromide, those. In those atoms, the p state, there are 6 places, but there are only 5 electrons. So when the 6th one go into it, it becomes a negative ion, actually, that negative ion has an energy that is lower than the neutral atom. That difference is called electron affinity. Okay? Now, we will need these two ideas, ionization energy and electron affinity, later on when we discuss ionic compounds. Okay, sodium chloride. So you may think that I need to put in some energy to take that electron out from sodium to form a sodium ion, sodium plus, that needs energy. And then that electron goes into chlorine, and that will give out some energy because that is the product has lower energy than the neutral atom. Will this be sufficient to balance the energy balance sheet, or what else will come in? And that is the physics behind ionic compound. Okay, so here we are looking at the periodicity feature. Nonetheless, these two ideas will be used again. Okay, the middle one is about nuclear atomic radius. You can get this by scattering experiments, scatter electron off. So I already explained these two ideas, so I don't need to go through this page, okay? But just to remind you that later on, we will bring them up again when we discuss molecules. And this page is meant to introduce you to something called the electron configuration. It's the ground state configuration. So it is related to filling in the independent particle states according to the power exclusion principle. There's a lot of quantum physics behind it. There's still a little bit we could not discuss here. It's so involved, all right? But let's say, for example, carbon. So we have 6 electrons. The first 2 will go into 1s2. So there is a 1s2 here. Okay, it's called a helium. So 1s2, then 2s2, then I am left with 2 electrons. They will go into the p state. That becomes 2p, and then there are 2 electrons there. So together with, usually the long form will be carbon. 1s2, 2s2, 2p2. Okay, so that is the ground state electronic configuration of carbon. So you see, as you fill in the thing, it will become longer and longer in describing what is the ground state electron configuration. The last column gives you the ionization energy, the first ionization energy that was plotted here. Okay, so it is in this plot. And then the periodic table is longer than 1 page, so it is the same thing. Let's zoom in on a few characteristic features as we move on through the periodic table. So we did a lot on hydrogen last semester and also this term. Then we discussed helium, so that 2 are done. So how about lithium? So lithium is something like that, okay? And this one can actually be up or down. Then you may wonder how to write this thing down in a legal way. All right, then you need a 1s up state, 1s down state. In this particular case, you need a 2s up state. You have 3 states, call them A, B, C, and you have 3 electrons, 1, 2, 3. Write down a Slater determinant, then you are done. That is the legal way. Okay. But let's look at some physics. the 1s are filled and they are closer to the nucleus. Therefore, they don't play much role in the chemistry of lithium. The chemistry of lithium is governed by this particular lonely electron. It is at a higher energy. It can easily be freed. The ionization energy is not that big. So that could become a lithium ion. And you know, lithium ion battery, things like that, the hottest topic now in energy engineering, right? Okay, so there's some quantum mechanical reason for that. Again, I would like you to work through the term symbol as long as you remember this is the symbol. So pair up, you don't need to worry about them, everything cancel. All you need to do is to do this. So this has to do with an S state, orbital angular momentum 0. So you have a big S in the middle. Okay, and then L is 0, you only have a spin half. Okay, S is half. 2S plus 1 is 2. All right, finally, L is 0, spin is half, the only J is half. So you have this. This is the ground state term symbol. Okay, but at least it's shorthand notation that you can communicate with the professionals, the chemists. Now, beryllium, the next one. The ground state should be like that. Okay, then one may think it is rather inert because everything is paired up. Nonetheless, it is active because there is nearby a 2p, which is empty in the ground state, but it doesn't need much energy to promote one electron to a higher state. Thereby, this can form a bond with something, come close to it, and so on. All right. So later on, we will have a very interesting discussion, I would say, about this thing. This exists. Beryllium bond with 2 hydrogen, and it's a linear molecule. Okay, so it's something like H, beryllium H. Okay, and then more interestingly, this length, so-called bond length, is the same as this. So you may think, if one electron is in 2s and another electron is in 2p, they should be slightly different. So maybe one side bond with the hydrogen electron will be different from the one on p bond with the hydrogen electron. But it turns out that it's symmetric. I mean, the beryllium in the middle, the 2 hydrogen, you look at it this way, you look at it the other way, they're the same. Okay, so what happened there? Maybe some of you already heard about this idea. I don't know whether you heard about this term before. It's called hybridization. In this, in the example I just mentioned, you will see later on, it has to do with sp hybridization. Okay, and the starting point. Someone heard about it in chemistry course, 1070 or something. Okay, but we will have a much quantum mechanical discussion on that. It is a quantum mechanical discussion. Okay, so you will see it is highly quantum mechanical. Then, after beryllium, we will start to feel the 2p level. So from element number 5 to number 10, there are 6 elements. Then we feel one by one all of this. and then we have this row of element, and then we end at neon. It is the first below helium. This is the one below helium, and it has a closed shell, and it is an inert gas, so-called, or noble gas. Okay, so this is an inert gas. It doesn't do much about chemistry. It doesn't like to bond with anything. But fluorine is active, very active, as we already mentioned. Given this one more electron actually has a lower energy than a neutral atom, that difference is called the electron affinity. You already saw this periodic structure, okay? But if we want to understand or calculate the electron affinity quantum mechanically, I hope at least you realize these are two different calculations for the reason they have different Hamiltonians. Do you understand? Different number of electrons. The Coulomb term will be different. So you need to do two Hartree-Fock-like things like that, calculations, and then compare the ground state energy. And you realize that fluorine ion is lower than the atom. The difference is called the electron affinity. So it's nothing trivial about it. It's quite quantum mechanical. I always think that if you want to learn physical chemistry and you don't have quantum mechanics at our level, it's quite a joke, I would say. So now we encounter a problem immediately. I'm talking about this row. Okay. Now, for example, carbon. We have 2 electrons to go into 6p state. How to do it? Is it random to put them in, or is there a rule that will give us the lowest energy way to fill the electrons in? So this is the question I'm trying to pose here on this additional page. So you have 2 electrons. Then if you just count the way to do it, there are 6p states, right? Then there are 15 ways, right? Statistical physics here, right? So how many ways? Then you do balls and stick counting. There are 15 ways. But then the question is, which way should be the lowest energy? A clever way or a silly way to answer the question is, fine, fill it in first, write down the wave function slated determinant, do the expectation value of the Hamiltonian, then you know the energy. You try every one of them, the lowest one will be the answer. If you think about it that way, good for you. Actually, that is the way to do it, okay? And fortunately, someone did that for you. It's called Hund's rule. Hund's was a student of Max Born again, you know, the big Born interpretation, a lot of things, Heisenberg's advisor, okay, when Heisenberg discovered matrix quantum mechanics. So he was another student of Born. So basically what Hund's did is he tried all this calculation, different arrangement to put 2 electrons, for example, about this, okay? And then this is one way, and how about this, how about that, and then another way. And then at the end, he summarized all his discovery in 3 rules. That is what is called the Hund's rule. We are not going to discuss deeply what Hund's rules are, but I just want to tell you that there was someone who already did this and summarize the result in some rules. Now we have 6 p state. You know that p states means L is 1, ML is 1, 0, minus 1. And this has to do with Y10, Y11, and Y1 minus 1. Do you know what I'm talking about? Spherical harmonics. So that, okay? Now, this is automatically pointing at Z. This is called PZ. But these other two things are complex. Then, if we form linear combination of them, plus minus I something, okay? And then we will get PY and PZ. So we have 3 spatially oriented PX, PY, PZ state. Next, we have spin being up, down, MS being plus minus half. And all together, we will have 6 P state, okay? So here I try to depict it this way. So I have this PX, PY, PZ. The question becomes carbon. I have 2 electrons. Should I put the 2 electrons all in PX, up, down? That is legal, not breaking Pauli exclusion principle, but is it the lowest energy way? Or should we put it this way? Okay. Similarly, when you go to higher, lower in the periodic table, that is to say, higher in the the atomic number, go into the D state is even more troublesome. So you have 5 D states and spin up, down, there are 10 places. If you have 4 electrons, what to do? Is this lower energy than that? Okay, the answer is this has a lower energy than that, and therefore we have ferromagnetic material. We have 4 aligned spin. That will be a stronger magnetic atom. Okay, so that is what the Hund's rule says. The Hund's rule says this is better, this is better, and this is called the Hund's rule. Okay, but again, I would like you to get a sense. You need to do different quantum mechanical calculations at the end, find out which filling has a lower energy. But the common sense is that we rely on what we learn, although limited knowledge, but rely on what we learn in the helium case. So when we have this kind of things, we can think about the helium atom, right? So the spin part is like a symmetric spin part. Therefore, the spatial part will be anti-symmetric. Therefore, the electron will tend to avoid each other. There's always Coulomb repulsive part in the Hamiltonian. Therefore, that will be less positive for that term, lower energy. Basically, this is what the Hund's rule 1 and 2. There are 3 Hund's rule, by the way. Hund's rule 1 and 2 said, this is the physics. So the physics is not new, but the calculation will be involved. Nonetheless, you can write down a slatted determinant for this, slatted determinant for that, find the expectation value of the Hamiltonian. At the end, you will discover what Hund's rule said. Then we move on to the next row. After lithium, then it is, after neon, then it is sodium. So you start filling 3s1, 3s2, 3p1, and then up to 3p6. So here again, you have to exercise Hund's rule, pair up first until run out of a single spin place, then you start pair up the 4th electron. Then we will encounter the 3D filling. And that is interesting because these are the very useful thing. I think this field are the very useful thing in terms of magnetic materials, manganese, iron, cobalt, nickel. Okay, but one in chemistry, it turns out this so-called transition elements, 過渡金屬啊，過渡金屬, they are chemically rather similar to each other. They have similar chemical reactions with other things, although they are different elements. We have a good way to understand that. The way to understand that is that the 4S, let me see, I did the configuration table. Here. Okay. So notice that we are talking about this part. Okay. So here, it turns out that the 4S is aligned in lower energy than the 3D. So the 4S was fielded first, and then you start filling in the 3D one. Okay, so the 4S in terms of the wave function extent from the nucleus, the 4S wave function is farther away from the nucleus. Then along these transition elements, we are filling another electron into the deeper level of 3D. So-called deeper means closer to the nucleus. So we are adding electrons into a stage that lives closer to the nucleus, leaving the 4S electron untouched. But the farthest away, the 4S electrons are responsible for sensing whether there are other electrons in the neighborhood to do wave function overlap. When you have wave function overlap with the other atom, there will be bonds forming, chemical bonds. That is the part in molecular physics that we will be discussing. The point now is because the 4S is the one that is extended further away, the chemistry is governed by the fielded 4S, while over this row, electrons are fielded into the inner 3D levels. Therefore, these transition elements, transition metal elements have similar chemistry. Again, many quantum mechanics facts are involved. So I already give this example. So if you have this 5D levels, and each one can carry 2 electrons up and down in it, when you have 5 electrons in d orbitals, which way is the lowest energy filling? It turns out that Hund's rule says, up, 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 that will minimize the energy, okay? So the rule says, it's called Hund's rule 1 and 2. The rule says, first, maximize the total spin. So up, 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 up will give you the biggest alignment that will maximize the total spin. Okay, so that is Hund's rule number 1. Then after the transition metal in the periodic table, you hit at something also very useful. You will soon hit at something called gallium, germanium, arsenide, what is this? Selenium. So these fields are very important in semiconductor industry. For example, germanium, above germanium is the famous silicon in the periodic table, okay? Silicon is above germanium. So these are elemental semiconductor, meaning by themselves, they don't need to form a compound, they are semiconductor. Semiconductor has the following property. Well, how to say that? if we solve the Schrödinger equation for electron in a periodic potential, we will get bands separated by band gap. We use Pauli exclusion principle to fill the electrons in. Then it depends on what happened after all the electrons are filled in. Semiconductor has completely filled band and separated by completely empty bands. That is the case for both semiconductors and insulators. Semiconductors will have smaller band gaps. That is to say, maybe by kT thermal energy, it is possible to excite some electrons across the gap into the empty band up there, so that they can become freely moving electrons to conduct, to give you all the devices. So that is semiconductor. And now the most important compound semiconductor is formed by these two things. It's called gallium arsenide. I think some of your device, laser pen, things like that, they are formed, they are manufactured by these compound semiconductors. Okay, so the periodic table as you go down remain very useful. So the last page, let me summarize. I hope that you appreciate the goal of our course. In the first part, we introduced some perturbation theory, writing things in a big matrix, variational principle. Then we move on to discuss atoms. Part 1, we put hydrogen atom into some and consider some small effect beyond the basic hydrogen atom. There are observable effects, Zeeman effects, spin-orbit interaction, and then we found that we can handle them rather easily by perturbation results. On the way, we also learned some formal quantum mechanics. For example, in spin-orbit interaction, we learned how to write down the Hamiltonian, that term, and also how to add two angular momenta in quantum mechanics. And we also discussed what formally quantum mechanics angular momentum means. After that, we also did some relativistic effect. We also did the fine structure and the hyperfine structure. Then we move on to other atoms. The other atoms, the best one to study is helium. Again, we use perturbation, variational calculation idea. We explore there are very highly non-trivial implications. For example, when we do variational calculation, it will give us a very powerful way to solve for independent particle states, namely the Hartree and more involved Hartree-Fock way. In addition, when we do this, we also realize that the spin, triplet and singlet state will be different due to something called the exchange integral or the indirect Coulomb integral. And that go all the way to the source or the origin of ferromagnetic interaction that give rise to magnetic materials that we use in our daily life. So in this summary page, I just want to reiterate the powerful and yet simple quantum mechanical tools that we build up. So first of all, quantum mechanics is the key to understand atoms. Although many of you don't like chemistry, that's why you choose physics, I believe. But at this point, I really want you to appreciate, now you are equipped with the proper quantum mechanics to understand chemistry. Okay? And then we realize that very complicated interacting many electron system may be reduced to single electron problems. And they are not doing lousy drops because of this self-consistent idea. Actually, that is basically the best way in the market. Then we discuss the antisymmetric requirement of many electron wave functions. That is a general principle, and how to realize it in single particle state, the Slater determinant. The Slater determinant form automatically tells us the Pauli exclusion principle. You learn that in high school, you learn that in general chemistry course, but the origin of it is deeper. It has to do with antisymmetric requirement of many electron quantum mechanical wave functions. At the end, we realize that with all these simple tools, reducing it to atomic orbitals, single particle states, Pauli exclusion principle, and supported by many quantum mechanical ideas, can explain much of the physics of atoms and the periodic table. Okay, so, and actually that is a big part of quantum chemistry. So that ends the module of physics of atoms, and this is also the cutoff point on the coverage of our midterm exam that will coming up in 2 weeks' time. Okay, I sent an announcement out yesterday. So for the remaining few minutes, I would like to motivate what we are going to do next, and then we will do something more seriously next week on time-dependent perturbation field. So the next module is shorter, but it is not less important. It is just as important, because we are going to do a brief introduction into a big topic. It is called more generally light matter interaction. No matter what your interest lies, this is at the heart of all physics. If your interest is in particle physics, particles had to do with matter part, the standard model, but there's light in it, the mediate particle, the particles that mediate interaction. Photon is the one that has to do with light, okay? Now, but ordinarily, back to atomic physics, molecular physics, solid state physics, if you don't prop the atom, you don't know anything about the atom. That's why in the 19th century, the whole atomic physics and later on quantum mechanics was established based on observation of spectral lines. Spectral lines means light is coming out or absorbed. This is atom-light interaction. So this is the topic of the next short module. So we will study why there are absorptions and emission of light by matter. On the way, we need to learn a little bit, not the full form of time-dependent perturbation field. That will be another approximation method that I will equip you to move on in your study later. We mentioned several things before in our atomic physics module. For example, we mentioned selection rules, transitions, delta ML equal plus minus 1 and 0. They are allowed, okay? But then other things not allowed. All right, so why so? What is the quantum mechanical origin of it? You will get the answer soon. We also know that for an atom, there are some energy difference between ground state, first excited state, second excited state. We must buy a good light source with the right frequency. H bar omega of the light must hit this difference so that there will be an absorption. Why so? Can we get that from quantum mechanics derivation? The answer is a yes. And that has to do with this thing again. And then in the spectrum of an atom, some lines are very bright, some lines are dimmer. Okay, why so? That has to do with whether the absorption occurs readily or with a tiny probability. Okay, again, can we explain that by quantum mechanics? That is the very important questions we are going to explore in this new module. So just some big picture. So what we are going to study is something like this. I have an atom. The darker line is the state that the atom is in. So like the atom is now in the 1s state at some time called negative time. But time equals 0 is the time that the light comes in, okay? It doesn't mean the birth of the universe, right? The Big Bang, okay? No, it is just some arbitrary time. So before light comes in, it is in the ground state called 1s, initial state. Light start to come in at this time. At some later time, it maybe go up to the final state. So if that occurs, we think that the atom is now excited to the final state by absorption. We need some light to stimulate the absorption. So formally, we can call it stimulated absorption. I think you have heard something called stimulated emission, right? So initially, the atom is here, light comes in, finally the atom is there, but with 2 photons out, that is called stimulated emission. That also happened. We can understand it by our time-dependent perturbation field. The big picture is as follows. When we have something like this, we don't have an isolated atom anymore. Before this point, we always think about an isolated atom. We have the Hamiltonian of the atom. And we know how to solve the time-independent Schrödinger equation for the atomic states. But once we think about light interacting with an atom, we have an additional term in our Hamiltonian. We have a light interaction, atom-light interaction term. And light comes in, and you know, light is oscillating electromagnetic fields. The E field goes up and down, the B field goes left and right, and it's propagating towards you, okay? So there is a time here in the oscillating E field. That's why we need a new approximation method called time-dependent perturbation field. We need first to introduce to you what is this new interaction term. How does it look like? What does it involve? It must involve 2 things. Some variables of the atom. More explicitly, some variables related to the electron in the atom. That is the matter part. And then the E field of the EM wave. That is the light part. So in this matter-light interaction, both variables in the 2 separate entities, matter and light, must appear. They interact. Okay, because light is oscillating in time, we have time here, and thereby we need to do time quantum mechanics. Quantum mechanics with time is easy to do. There's only one equation, no other choice. It is time-dependent Schrodinger equation. So the whole module that follows has to do with how we can apply this time-dependent Schrodinger equation when we have such a Hamiltonian, given that at initial moment, this atom is in some initial state. This comes in after time t. What is the probability the atom is now found to be in an excited state? That will be the question that thread through the whole module. If we can find that probability, then we can find out whether that line will be very bright or very dim, or that line will not occur at all. That is, it does not obey some selection rule. Okay, so we will explore this problem next week. Okay, so long for today, and then I will stay on. If you have questions, please ask.